we've looked at estimating a population mean based on a sample mean. And the way we did that was we assume that we have a Gaussian distribution. So if we don't in fact have a Gaussian distribution, then our conclusion isn't valid. So we want a way to test to see if that assertion that we have a Gaussian distribution is good. And we can use the chi-square test. We can also use this to test other hypotheses. So we'll look at one in a minute for tossing a coin. So if we have the hypothesis that we have a fair coin, then we can test that with this fit. Because in that case we would assume a 50-50 distribution of heads and tails, and then we can use the chi-square test to see if our measurements fit that model. This is the definition of chi-squared. We have measurement x, the observed value, and the difference between the observed and the expected value. We square that, divide it by the expected value. And we take the sum of all the trials that we have, so all the observed values that we have, and that's chi-squared. Whenever we perform the chi-square test, we need to know what the degrees of freedom are for our data. And here's a way of figuring that out. So degrees of freedom f is the difference between the number of categories. So that would be I equals 1 to n, so n is the number of categories. And then k would be the imposed conditions, so the constraints. And we'll look at some examples of n and k so you get a better idea of how to assign values to those. Once we have our data and we found chi-square and we know what the degrees of freedom are, then we use this table, and this will give us the probability that the differences here between observed and expected are due to just chance, so that they're due to random factors. And again, all this will be clearer when we work through a couple of examples. Say for this example we flip a coin 20 times and we come up with 5 heads and 15 tails. Well, what we want to do is test if Jimmy is giving us a fair coin or if it's a loaded coin. So we use the chi-square test to see if the coins that Jimmy's given us are fair or not. And one note about our test: if we come up with fewer than 5 in one of our categories, then we need to redesign it. So here we calculate chi-squared. See, we have n equals 2. So there are 2 different ratios that we're taking here. 5 minus 10. 10 is the expected value of heads. 5 is the observed value, squared divided by the expected value. And then the same thing for tails, so 15 minus 10 over 10. Right, so that gives us chi-squared is equal to 5. Now degrees of freedom. Again, like I said, we have 2. Number of categories is 2, so we've got heads and tails. But then we have a condition here, and that condition says that the number of heads plus the number of tails has to equal 20. So we're taking away 1 degree of freedom. So we have 1 degree of freedom. And now we'll look here on our table. We find the row for 1 degree of freedom, and we go over until we find the corresponding value for chi-squared. And it's really close to 5.02. And this tells us that we have a 2.5% chance that the discrepancies here, where our observed deviate from our expected, is due to random error or random factors. So there's only a 2.5% chance that the difference here between what we expect is due to random causes. So that means that there's a 97.5% chance that there is some definite factor causing this not to fit what we expect. So there is a limit to the probability at which we can, or beyond which we accept a theorem or reject a theorem, and that's usually 5%. So if our probability is greater than 5% that the discrepancies here are caused by chance, then we will accept the theorem. If it's less than 5%, that's often the criteria for rejecting the theorem. So our theorem here dictated what our expected values were. So our theorem was that we had a fair coin, that Jimmy gave us a fair coin, and we have we need to reject that because we only come up with a 2.5% chance. All right, so let's see what would happen if Jimmy protests and says, no, I always give you fair coins. Here, try another one. So we take another coin from him and we toss it 20 times. And we end up with heads and tails and observed and expected. So we observe 7 heads and 13 tails, and of course we expected 10 and 10. And then we can combine that with our earlier trial where we had heads, tails, observed 5 and 15 and expected 10 and 10. And now we can see if we come up with a different probability now that we've run this second test. Okay, so here's the new one and here's the first one. Now we can recompute chi-squared. So chi-squared, again, we've got 7 minus 10 squared over 10 plus 13 minus 10 squared over 10 plus 5 minus 10 squared over 10 plus 15 minus 10 squared over 10, which is 0.9 plus 0.9 plus 2.5 plus 2.5, which equals 6.8. So now we have chi-squared as 6.8. And let's see about the degrees of freedom. All right, so we want to tally up the number of observations we had, categories, so that was 4. So it's n minus k. So n is 4, and then k is the number of constraints. So here we're saying that this and this is 20, and we're saying this and this is 20 also. So we have 2 constraints. So we have 2 degrees of freedom. Now let's refer to the table. And again, now we're going to use this different row because we have 2 degrees of freedom, and we want to see what the probability of chi-squared being 6.8 is. So we come over here, 6.8. So we're somewhere between 5.99 and 7.38, which means we're somewhere between a 5 and 2.5% chance of an unbiased coin, or a 5 and 2.5% chance that the discrepancies we see were caused by random causes. So again, we're going to reject our theorem that Jimmy is giving us fair coins or unbiased coins. And in this example, we had 4 observations and there were 2 degrees of freedom that we took away. We had 2 constraints. So the number of observations here and the number of trials here. And we used our model that we wanted to test to get an expected value, and then we compared that to the observed value to get chi-squared, and then we found the degrees of freedom and used the table in order to come up with our probability for chi-squared being due to random factors.